Hey students, in this video we're going to review exponential functions. So the first thing to understand is an exponential function is used to model repeated multiplication or division. The basic form of an exponential function is y equals a, which is our initial value, times b, which is our growth or decay factor, our multiplication or division, to the x power. We use an exponent to show that this multiplication is happening repeatedly x number of times. A few conditions on this. A cannot be 0. The reason why a can't be 0, I'm going to actually show you a graph. Okay, so before I show you why a can't be 0, let me show you an example of an exponential function that meets all the requirements. So here I have x being the input, and I have the function is 3 times 2 to the x power. So my initial value, which is also represented as my y-intercept on the graph, is at 3. Then, for each x value, my function's values are being multiplied by 2. So 3 times 2 to the x power. So when x is 1, I've multiplied 3 by 2 one time. When x is 2, I've multiplied 3 times 2 two times. So 3 times 2 is 6, times 2 again is 12. Okay, I can also go backwards into negative values. To multiply by a negative amount is actually to divide by 2. So 3 divided by 2 is 1.5. 1.5 divided by 2 is 0.75. So here's an exponential model, and we can see these points plotted and why this exponential model happens based off of this repeated multiplication, or if I go in the backwards direction, repeated division. So if I were to make my a value 0, then my initial value is 0, and if I multiply 0 by 2 repeatedly, I'm just going to stay at the value 0. So when a is 0, this is actually not an exponential function. This is a constant function at the line y equals 0. The other rules is that b has to be a positive number and not 1. If b is a negative number, then we're multiplying by a negative number repeatedly, which means we're bouncing back and forth between positive and negative values. This is not going to create an exponential function, so b can't be negative. B also can't be 1 because if I multiply repeatedly by 1, if I start at 3 and I multiply by 1 on repeat, then again, I'm going to have a constant function at the line y equals 3. And then sometimes we have what's called a base of e. E is a number similar to pi. It's roughly about 2.7. E is a number that we use often for what we consider continuous growth. It's not quite doubling, it's not quite multiplying by 2, and it's not quite tripling, multiplying by 3. It's kind of somewhere in between, and we use this for continuous growth. So again, multiplying by this value e over and over and over again, or if I want to go backwards, dividing by e over and over and over again. We say that exponentials are exponential growths if our multiplier b is greater than 1. This will make the graph increase away from a horizontal asymptote of y equals 0. Again, it'll make this function grow. We can have a domain of all real numbers, so you can take any value and plug that into your x. But the range is going to be greater than that horizontal asymptote. So wherever the horizontal asymptote in the graph, the range is always going to be greater than that value. If for whatever value the b is, the amount over 1 is called the percent growth. If the value of b is between 0 and 1, so a decimal like 0.5 or 3/4 or something like that, if it's between 0 and 1, we would call this an exponential decay. What this means is that the graph will start at a y value and it is going to decrease towards a horizontal asymptote of y equals 0. The domain is still going to be all real numbers, and the range is still going to be everything larger than that horizontal asymptote. However much under 1 we call this the percent decay. So it's always in comparison to 1. If we are over 1, we call that the percent growth, and if we are under 1, we call that percentage the percent decay. Okay, for this example, we're going to talk about the key features of this exponential function. We're going to create a table and a graph for y equals 16 times 1/2 to the x power, and then we're going to determine the following features: domain, range, increasing or decreasing, the intercepts, the asymptotes, and the end behavior. For time's sake, I want you to create the table and the graph of this function on your own. See if you can take a moment creating the table and the graph for this function. Okay, I started my table by using my initial value of 16, and then for each x value, I took half of 16 repeatedly. So half of 16 is 8, half of 8 is 4, half of 4 is 2. To go backwards, I'm doing the reverse of taking half, which is multiplying by 2, and then I created my graph from there. So again, my initial value is also my y-intercept. Initial value is my y-intercept, and this 1/2, the fact that I'm taking half is making my function overall decreasing. So let's start talking about some of my key features. The domain of my function is all real numbers. The range of my function is everything above my horizontal asymptote. I have a horizontal asymptote of y equals 0. So my range is going to be everything from 0 to infinity. 0 is not included here because I'll never actually reach 0. As I continue to take half, I'll go into decimals, but I'll never hit 0. Because I'm taking half, this is decreasing. My x-intercept is my initial value of 0, 16. And the end behavior of this function is as x approaches infinity, the limit of my function y is 0. It approaches that horizontal asymptote. And as x approaches negative infinity, the limit of the equation y is positive infinity. It goes up to infinity as I go backwards in my x values. One thing that I didn't ask for, but I think that is also important, is to talk about the percent change. Because my multiplier is 1/2, 1/2 is 50% less than 1. So we would call this a 50% decrease. Okay, so it's important to be able to identify the key parts and elements of these exponential models. So we'll take a look at the first one and maybe do the second one as well. So number 1, I have the function y equals 12 times 1.03 raised to the x divided by 2 power. We know that x here is measured in days, so this change, this multiplier, is happening per day. Okay, so let's take a look at some of our key features. The number out front is always your initial value. Your multiplier tells you whether this is an increase or decrease. Because my increase is greater than 1, in fact, this is 0.03 greater than 1, this means this is going to be a 3% increase. And then the fact that my x is being divided by 2, this means instead of happening each x value, this is going to happen every 2 x values. In this case, every 2 days. So this change happens every 2 days. Okay, let's take a look at number 2. I have y equals 7/3 times 0.892 times, or raised to the 4x power, and x here is measured in hours. So again, my initial value is 7/3. My change factor is less than 1, and to figure out how much less than 1 it is, I'm just going to subtract it from 1. So it's less than 1 by 0.108, less than 1. Turning that into a percentage, I can say that that's a 10.8% decrease. And then because my x is being multiplied by 4, my change happens 4 times per, in this case, hour. Okay, try the last one on your own. Okay, I said my initial value is 6. My multiplier 3 is 2 units greater than 1. So multiplying by 3 is actually a 200% increase. And then the change happens every 9 centuries. My unit of time here is measured in centuries, and I'm dividing this by 9, so it happens every 9 centuries. Okay, here are some important application formulas that we use often with exponential functions. So the most common one is just a percent growth and decay. You have your initial value, you have your starting amount. So 1 says that you're multiplying a by 1 and then plus or minus some rate of change. This rate of change will be a percent as a decimal. So it'll be greater than 1 if it's growth, and it'll be less than 1 if it's a decay, raised to the time power, where t is time. Our compound interest formula and our continuous compound interest formula deals with borrowed money and the interest that that money either gains, or the interest that you earn in the bank gets compounded. So if you earn a little bit of money and interest, that gets added to your current pot of money, and then your interest compounds on top of the money that you're earning. So we use this formula when we are specifically told a number of compounding. So this n is representing how many times the thing is compounded. So n being 4, this would be 4 times a year. Your interest gets added back to your principal, which is your P, your initial investment, 4 times a year. Or maybe it gets added daily. Your interest gets added daily, so that n would be 365. The n is the number of times that the compound gets paid into the principal, or the initial investment amount. And then continuous compound means for every cent that you earn, it gets immediately added to your principal. So we use what's often sometimes called the PERT formula. P, your principal, which is also called an initial investment. E, which we talked about at the beginning of this video, which is used to show continuous growth. Your rate, depending on how the interest rate that you're paying on, and T, time. So let's take a look at some examples of this. So you deposit $3,000 into an account that pays you 3.28 annual interest. How much would you had if your interest was compounded daily for 5 years? Okay, so what we're going to do is we're going to start with our initial formula, and then I'm going to fill out that formula and explain what they mean. And this should say question 1. Okay, so our amount of our investment A is equal to our initial investment, in this case, our principal amount of $3,000, an account that has an annual interest rate of 3.28. Now, anytime you have a percentage, you do need to convert it to a decimal. Easiest way to convert this to a decimal is to divide by 100, but this is your interest rate, your R. So we're going to do 1 plus that interest rate. Now, because this is an annual interest rate, we are compounding this daily. So this annual interest rate has to get divided by, the annual interest rate has to get divided by 365, because that's your daily compounded amount. So my N here is 365. So I'm dividing my annual interest rate by 365. And in addition to dividing my annual interest rate by 365, I'm also going to have to multiply my time by 365. So it's been sitting in my account for 5 years, meaning T is 5, but it can't just be 5 times, because every time I compound, I'm also increasing my percentage. So this is 365 times the 5 years. So a total of quite a bit of compounded interest there. Okay, so this is all numerical. I can type all of this into my calculator at one time. So I'm going to take a second and do that. Okay, so that means that in this 5 years, my investment of $3,000, because of the compounded interest that the whatever bank you're putting in has been paying you, so this gives you a new principal amount of $3,534.62. If I want to do the same process, but they're telling me that it's compounding continuously, then I would use that A equals P e to the RT power, where my principal hasn't changed. I'm still using $3,000. The multiplier now is this value e, which is that 2.7, roughly 2.7, raised to my interest rate. Again, use that as a decimal, so 0.0328 times the time. Again, it's been 5 years. So this is another calculation, and this is if you compound continuously. And I can type that in to find that value as well. And using this type of compound interest where I'm compounding continuously, this would give me a value in my account after the 5 years of $3,534.64. So the more you compound, the more money you make. It's only a 2-cent difference, but continuously is more valuable than compounded daily. Okay, the last question that we'll do is another word problem. We have the population of Texas in 2003 was 17 million people. Population grows at 5% every 2 years. Write a function that models the population growth of Texas since the year 2003. So the first thing I'll do, create a little bit of space. So I'm going to model the population. So I'll have my output P. You could also do Y, doesn't matter. Is going to be equal to the initial population of Texas. In this case, my initial year is 2003. So this is when X is 0. And my initial population then is 17 million. Rather than writing all the zeros, I'll do this in terms of millions. So I'll just use the number 17. Then I'm going to multiply this by my multiplier. Since it is growing at 5.5%, I have to do 1 plus that interest rate or that rate. Again, the rate is a percentage, so it does need to be converted to a decimal. Dividing that by 100 gives me 1 plus 0.055. And then this is going to happen every 2 years. So in my exponent, instead of happening every year, X, since the year 2003, I'm going to divide that by 2, saying that it happens every 2 years. So this is my equation that models this phenomenon. Again, the every 2 years, I have to divide my multiplier, my exponent by 2, so that this change happens only every 2 years. B says, based on this model, what would the population be in 2018? This is 15 years after 2003. Well, X is our years since 2003, so I can just plug that in for my X value. Take a second to write down what P and X stand for. And I can type all of this into my calculator one time. So I got a population of 25.4. Remember, population is in millions. So this is 25.4 million. And then in question C, it says, based on this model, when will the population just be 25 million? We're going to solve this by graphing. So we want to know when will the population, so when will P be 25 million, excuse me. And we'll actually use Desmos to solve this equation by graphing. In a future video, we're going to learn how to solve this by hand, but for time's sake, we'll just solve by graphing. And this happens exactly at 14.4 years. Okay, that's it for this video. We'll do more practice with this in class tomorrow.